Hello guys, in this video I'm going to show you some more examples on vector spaces. So we have actually seen three examples. We started with three examples when I started vector space, but here we are going to see some more examples, and it is going to be some non-intuitive examples. Okay, so we'll see that. So let us see the summary. So I said that vector space has four things. So there is V set V, which are the set of vectors. Then there is a set F or a field F. So field is the right word. So field F. Then there is vector addition and scalar multiplication. So if you have these four things, you can say that you have a vector space. Okay, the elements of the set V are known as vectors. Okay, so let us see the most intuitive example, the n-tuple vector space. So here you just have n numbers where each of these numbers belong to R. So x1, so V is a set of n tuples such that each element in the tuple belongs to R. So x1 is a real number. It comes from a set of reals. Similarly, x2 is a real number, and so on. And like this, you get a n tuple. So this vector kind of a thing. So our notions of vectors is actually this, right? So this kind of thing is actually known as a tuple. So this is an n-tuple thing, and over here I can say the field is real numbers. Okay, and plus means addition component wise. That means if I have two vectors, say x1 x2 x3 till xn, and some y1 y2 y3 till yn, so addition will be x1 plus y1 x2 plus y2 and so on. And dot means scaling. So what does scaling mean? So you just multiply a element that comes from the field over here, and that particular number will get multiplied to all of these. So that is scaling. How does the vector look like? The vector looks like this for this vector space. So we will see this will change as I change the vector space. So for this vector space, this is how the vector looks like. Okay, so a visual representation for this a set R2. So that is, I have now only two elements. The tuple is a two tuple thing element, and here the field is R. So this is how you can represent a vector. So there is a 0 vector over here, 0 comma 0, and there is some A which has x comma y. Alright, so over here x comes from the set of vectors V. So in this case it is R square. Right, so this was quite intuitive, but let us see some non-intuitive vector spaces. So this is one of that. So vector space of periodic functions. Okay, let us just revise what is a periodic function. So periodic function, so f of x is a periodic function if f of x plus n t naught is equal to f of x. So what does this mean is, if you take any value of x, say this is a sine wave that I've plotted. So let us take the value of pi by 2. Let me have the right. So let us take this value for now. Say this is pi by 2, right? Pi by 2. Okay. So now we know that at this point of time sine is 1. The sine pi by 2 is 1. Now, so over here, let x be pi by 2. Okay. I don't know why I wrote pi over it. That's okay. So pi by 2. Okay, so x is pi by 2. So what this function says is, you do f of pi by 2 plus n times. So n is any real number. Sorry, n is any integer. So here you can see 1, 2, 3. So it cannot be a fraction. So n is any number, I mean integer, into t naught. So what is t naught? So over here this is t naught. Okay, so over here, oh okay, so let this be pi. Right, so over here t naught is nothing but 2 pi. right? So what this says is if x of pi by 2 plus any n into 2 pi gives you the same as f of x, that is f of pi by 2, then it is called a periodic function. So the function will always repeat after a certain interval of time. So f of x, that is say f of pi by 2, is same as f of pi by 2 plus t naught. So this is t naught. Right, now this is also true if you do 2 t naught. So this was pi by 2, you do 1 t naught, you do one more t naught, again you will get 1, and so on. So like this, you do any n t naught, you will get the value as same as f of x. So this is right. So over here this is t naught, so you can have anything as t naught. So just wherever you see this is repeating, that thing you can say as t naught. So this thing is equal to this thing, right? I hope this is clear. Okay, let us go back. Right, so we saw what is periodic function. So let V be a set of all the periodic functions that one can imagine with a period of t naught. So this is very important. The period should be same, period of t naught. Okay, and the field, say f is belonging to R. Let addition means pointwise addition. So what I mean by pointwise addition is, so let us go over here and see that. Okay, so if I have a function like this and I have one more function which is say I don't know, something like this. Okay, so pointwise addition means uh, the addition of these two functions will be this at the point at this point plus this. So the function will get added at every time instant and you will get some other function. Okay, so we'll see this more nicely when I go to the graph, that is Desmos. Right, so what this says is if you have a V which is set of all periodic functions with a period t naught, your field is from real numbers, addition is pointwise, this is scaling, this normal scaling, then this thing is also a vector space. Okay, a vector looks like this. So now your vector is actually a function. So please understand this. Over here the vector was an n-tuple, but over here the vector is a function, because for this vector space the vector becomes a function. Hence I have given emphasis on the vector is actually the element of the set V. So whatever is the element of a set V, that will be called as a vector. So normally we have a notion of this thing to be called as a vector, which has square brackets and which is like, but with from linear algebra point of view, anything can be called as a vector which has the set V. So any element of the set V is called a vector. So it depends on which vector space you are, and that will define what will be or how will the vector look like. Okay, so x is equal to f of t. So over here vector is a function, and over here actually it is a periodic function. So over here x is a periodic function, that is a vector looks like a periodic function. Okay, let us just quickly go to Desmos to just intuitively understand is this true or not. Okay, so we are in Desmos. So over here I am going to just show you a lot of periodic waveforms. We'll add them and see what happens. Okay, so this is the sine wave that we all are familiar with. So this is the amplitude, so you can vary the amplitude of the sine wave over here. Okay, then let me put a cos wave then. So this is a cos wave, let me put both of them, and you can also vary the amplitude of the cos wave as well. Okay, then I show you a sec wave. So this is, let me just remove these. So this is how a sec wave looks like. Oh, here is its amplitude. So this is how the sec wave looks like. Then you have the tan wave. Okay, right, so this is how the tan wave looks like. Okay, and so this is the time period. So let me show you all the waves now. So these are the 4 waves that I'm going to show you now. So now if you change this, the time period of all the waves change. So this is one important criteria of this vector space, that the time period should be the same for all the waves that you have. Okay, now you can, now let me show you, just let me add them and let us see what happens. Is the time period changed or not? Right, so here I have added all the waves and this is what it looks like. So you see, when we add all these waves, we get some different kind of a wave. But then if you see, the time period is the same. If I just take a point over here and the other point over here, so this is the x coordinate and the y coordinate. So this is 1.6, this is 3.6. So I had the t naught as 2. So you see that the t naught is still 2. 3 minus 1 is 2. So no matter what you do, no matter how much amplitude you vary, no matter how much amplitude of the other wave you vary, the time period is always going to be same. So that is the output. This addition of all the vectors is again going to be a periodic wave which is having the same time period. So intuitively we can understand that if you have periodic functions with a period t naught, then you can have a vector space. So no matter if you add any two periodic functions having the same period, you'll get a third periodic function which is again having the same period. Okay, so hence we can say this is a vector space. Okay, next. So next, going into a little of signal processing. So finite energy signals. So finite energy signals are defined like this. They have the notation like this. So they are called as L2 of R. So over here everything is having a meaning. So L over here represents a function space. So over here again we are having a space of functions. So we are going to talk about functions. Second, R is the basically on what do these functions operate. So the domain. So these functions operate on real numbers. Okay, and then this 2 over here, this actually is representing a 2 that is over here. If this would be 3, there would be a 3 over here. If this would be 1, there would be a 1 over here, and so on. Okay, so what is the L2 of R? So it is defined like this. It is all those functions. So it is f of t, any f of t. So any function such that, so this means such that integration of that function of the mod of square. So since there's square, so there is square over here. So integration of mod of the square of this function from minus infinity to plus infinity dt is less than infinity. So intuitively, if you have a function over here, so the integration of the function from minus infinity to plus infinity, the whole area under this curve should be finite. It should not be infinite. So one example of how it will go infinite is as follows. So if you see an exponential curve, so this is an exponential curve. So for an exponential curve, you'll see that if I take the area from say minus infinity to plus infinity, you will have no bound. So this is infinite, right? So this kind of a function will not come in finite energy system signal. So any signal that is having finite energy, that is its area under this curve is finite, that we will say as a finite energy signal. And intuitively we can say that if you add any two finite energy signals, that is if there is a signal like this and then there is a signal say something like this which is again finite energy, so the area under this curve is also finite. If you add both of these, you'll get another finite energy signal. So this is quite intuitive. You'll see, you'll get a function which is something like this, right? So if you add any two finite energy signal, you get a third signal which is also finite energy. So over here you can see that a vector looks like this. So vector is actually a function. Again, a vector is a function over here, but over here it is finite energy function. In the previous case, we saw that for periodic function, it was a function which is a periodic function. Over here, it is a finite energy function. So for people who know what is Fourier transform, these functions are weak condition for the Fourier transform to exist. So Fourier transform does not exist for all the functions. So this is a weak a weak condition for the Fourier transform for it to exist. Okay. Next, let us talk about absolutely integratable signals. So over here, if I have a 1, so as I told you, there will be a 1 over here. So it is okay if you don't write the 1. And so over here now you are not squaring the absolute, the mod of the function. You're just adding them. That's all, right? So absolute is over here. In the previous case, there was a square over here. So this is the difference. That's it. And you see that if you have a set of all the absolutely integratable signals, then you'll see that that is also a vector space. You add any two absolutely integratable signals, you'll get the third absolutely integratable function. Okay, again you can have a scalar as well over here. So if you multiply with a scalar, so this will scale somehow like this. Sorry, not like this, but yeah, something like this. So it'll scale, it'll go up and down, but still it will remain finite. That is what is important. And this is actually the condition for Fourier transform to exist. So only these signals which are absolutely integratable, only for them the Fourier transform exists, and not for all the functions. So if you are a signal processing person, then you want to work with absolutely integratable signals, then you can define this as your vector space. Then whatever properties apply on vector space also apply on these signals. So that is the beauty of vector space or linear algebra, that you can use this wherever the pattern is followed, the vector space pattern is followed. So that's all for this lecture. I hope you understood. So if you have any doubts, you can always put them into the comments. And thank you so much for watching. Thank you.